I'm back with another related rates problem. This time I'm going to do a balloon. Now some of you have noticed that when you're blowing up a balloon, the rate changes as you blow it up. In other words, the radius is expanding out. At first it expands very rapidly and then it slows down quite a bit. Here's how it works. You'll notice right at the end, it isn't because I'm putting less air into the balloon, it's because the balloon is so much larger that it takes a lot more volume to expand it just a little bit. What we're going to do is look for how fast the radius is changing. Now the radius is going to change very quickly at first, and then it's going to change more slowly as it gets larger and larger. Again, this related rates are very easy to do. A little bit hard to follow and understand what's really going on. I'll see if I can do the calculations for you arithmetically as well to do the verification. Basically, here's what happens. I take a balloon and I'm going to try and blow at a constant rate. That's impossible, but I'll get it as close as I can. I want to inflate it at 10 cubic inches per second, and I want to know how fast is the radius changing when the radius is 3 inches. So I'm blowing into the balloon at a constant rate. And when the radius is 3 inches, this is about 6 inches across, so the radius right now is about 3 inches. At this point in time, how quickly is the radius expanding? Now we know that the volume is changing this way at 10 cubic inches per second. So all we have to do is write a relationship between the volume and the radius. The volume of a sphere, this is supposed to be a sphere, it's pretty close. And put a belt around it. The volume of a sphere is equal to 4/3 pi r cubed. And again, we're going to differentiate this with on both sides with respect to time. I'm going to take d dt of both sides. And what I end up with is dv dt. There it is. The change in volume over time. This is the instantaneous change. And I multiply the 3 times the 4/3 pi because we're going to differentiate this side. Take the exponent times the coefficient, and the 3's canceled with this 3 to give me 4 pi. R, reduce the exponent by 1 and you get 4 pi r squared. And I also have dr dt. That's what I'm looking for. I would like to know what this is. I want to know the instantaneous rate of change of the radius. In order to find it, I have to know what radius I'm interested in. I'm interested when the radius is 3 inches. I know what dv dt is. It's 10. This is cubic inches per second. This is 4 times pi. The radius is 3 inches. Notice that this is 3 square inches because I'm going to square it. When I multiply this, I get 10 cubic inches per second. This is going to be 9 times 4 is 36 pi inches squared times dr dt. Now what I'm going to do is I'm going to divide by 36 pi inches squared on both sides. And I'm going to get dr dt. The inches squared simplifies with the inches cubed to give me inches per second. This is 10 over 36 pi. Now this is a small decimal, fairly small decimal. Let me divide it. It gives me about 0.09. This is an approximation. This is an exact answer. dr dt is approximately 0.09 inches per second. So it's not expanding very quickly. It's going out at about 1/100th of an inch per second. Yep. About 1/10 of an inch per second, more or less. Not very quickly. Now you can actually test this in your calculator. You can take a look at what happens when you have a volume of when you have a radius of 3 inches, and what happens an instant later. And take a look at that arithmetic